Hi, everyone. All right. Hope you're doing well. We're going to continue our discussion by um, going on to talk about multi-electron atoms now. Our discussion here is going to be more qualitative because multi-electron atoms are so complicated that, well, we can't really do the subject much justice in this course, except to point out some of the broad features. Anyway, that's what we'll do. I want to start, though, by just reviewing what we've just learned about the hydrogen atom and comparing the Schrodinger picture to the Bohr model that we talked about previously. All right, hang on one second. Very good. So just to remind us of where we are, a few weeks ago we talked about the Bohr atom, and then in the last class we looked at the Schrodinger model of the hydrogen atom, okay? These are similar in some ways, but they're also very different, and I'd like you to appreciate it. And I thought we could do that best if we just go line by line and look at the different conclusions of these models. So a Bohr model, of course, is a semi-classical model. We solve the equations of motion to find the orbits of electrons using the postulate that the angular momentum is quantized in units of h bar. The fully quantum model is very different. Here we simply solve Schrodinger's equation to find the energy levels and the wave functions for the electron in the potential due to the proton, okay? Some things are quite similar. Rather miraculously, both models give the same values for the energy levels shown here. The energy is determined by the n or shell quantum number, and it's just minus ke squared over 2a naught, 1 over n squared. In the Bohr model, n and n was the only quantum number, okay? The energy was quantized and angular momentum was quantized, but both were just determined by n. In the Schrodinger equation, the energy is solely determined by n, but there are two other quantum numbers, the orbital quantum number L and the magnetic quantum number M, okay? And they have an important role in determining the degeneracy of the different levels of the hydrogen atom. Things get really different when we look at the picture that the model gives us. In the Bohr atom, we have this electron orbiting the proton in sort of a planetary model, if you like. Although we know there's something odd about this because we're also to think of the electron as forming a standing wave that encircles the orbit somehow, okay? But in the Schrodinger atom, we simply have a wave function that extends through space, okay? A three-dimensional wave function, okay? And here's a sketch of the probability density determined by that wave function in three-dimensional space. And here's the radial probability density that we get from this, okay? These pictures are extremely different, okay? And make sure that you're really clear on this. The Bohr model is wrong, and as far as anyone knows, the Schrodinger model is correct. And let's highlight another difference too. Here, what's the angular momentum of the electron in the ground state, the lowest energy state of the hydrogen atom, according to the Bohr model? And what is it according to the fully quantum Schrodinger model? Here, I'll put up a reading question so you can answer this. All right. Let's go on. So now, remembering how the hydrogen atom works from our last view graph, we can go on to talk about multi-electron atoms. Multi-electron atoms are different in several important ways. First, when we have more than one electron in the system, the electrons have to obey the Pauli principle. The Pauli principle says that no two fermions can be in the same quantum state at the same time, okay? And this sort of makes intuitive sense to us. What's odd is that there's another class of particles called bosons, and it's no problem to put more than one boson in the same quantum state. But anyway, electrons are fermions, and they obey the Pauli principle. Secondly, the electron-electron interaction modifies the potential that each electron feels. So remember, electrons repel one another, and that's important when we think about how the, when we think about the energy states of a multi-electron atom. In fact, this interaction makes the problem very complicated because we sort of have to know where all the other electrons are before we can find the potential that one electron feels. But of course, that's exactly the problem we're trying to solve. Where are all the electrons? So the problem has to be solved in what's called a self-consistent fashion. As you'll see if you ever, once you get to problems that look like this. Okay? All right, 1 second. Okay. One other thing we need to remember, one other thing to keep in mind is that electrons actually have another degree of freedom. There's a fourth quantum number for the electron in the hydrogen atom. And that denotes the electron spin orientation. We'll talk about spin a little bit later. For right now, we just have to understand that an electron in an orbital can also have either spin up or spin down. And this effectively doubles the number of states. Okay? All right. Let's look at the effect of this on multi-electron atoms. So first, imagine an energy diagram for hydrogen. We have the 1s state. We have the n equals 2 states, 2s and 2p, but they're at the same energy. And we have the n equals 3 states, 3s, 3p, 3d, again, all at the same energy. In a multi-electron atom, the interaction between the electrons breaks this degeneracy. That's one of the most important features. Okay? So the 1s state here is non-degenerate. But when we get to the n equals 2 states, we see that the 2p state is not at the same energy as the 2s state. Instead, it's at a higher energy. And this is effectively because on average, when the electrons are in 2p orbitals, they spend more time closer together. And so their repulsive interaction is greater. The effect is more highlighted for states with higher angular momentum quantum number. Here's 3s, 3p, and 3d. And now notice something interesting. In this generic multi-electron atom, the 3d orbital is actually higher in energy than the 4s orbital. So as we fill these states up with electrons, we can expect that the 4s state will actually fill before the 3d state. And this pattern continues. So for the n equals 4 states, 4s, which fills after 3d, but 4p fills after, fills next. But then the 4d electron states are higher in energy than the 5s states. So the 5s states fill before 4d. And then the 4f states fill later still, as we'll see in a moment. Okay? So this of course is important for explaining the structure of the periodic table, something we'll look at next. But it comes about because of the interaction between the electrons in the hydrogen atom. I'm sorry, the interaction between the electrons in the multi-electron atom. Okay? Something that's hard to, a problem that's hard to solve mathematically, although it can be solved, but one that produces these broad results. So we can use this picture to understand the periodic table. Imagine filling up electron orbitals with electrons. the first 2 electrons can go into the 1s orbital, spin up and spin down. But once we have 2 electrons in there, we can't put a 3rd electron in without violating the Pauli principle. So the next electron would go into the 2s orbital. We put 2 electrons into the 2s orbital here. 2s is filled, and the next electrons will go into the 2p orbital, okay? And we can put a total of 6 electrons into the 2p. At that point, the 2p orbitals and the n equals 2 shell itself are full, and the next electrons will go into 3s. 3s, we have 3p, and then you might expect that the 3d orbitals would fill next. But because 4s is lower in energy than 3d due to electron-electron interaction, the 4s states fill before the 3d states do. So we have the 4s states here, and then we get elements where the 3d shell is being filled up. After that, the 4p shell can fill, and then we get the 5s states fill, and then the 4d. And then the 5p shell fills before the 4f shell fills. 5p, even 5s. Only at this point, we have the n equals 6 s orbitals occupied, the n equals 5 p and s orbitals occupied. Only then do we start to fill up the 4f orbitals, okay? And the pattern continues throughout the rest of the periodic table. And as you all know, this is very important for determining the chemical properties of elements. First of all, the chemical properties are determined by the electrons in the valence or outermost orbitals. And for that reason, elements that are in the same column of the periodic table have very similar chemical properties, okay? But there's something else too. If we look at these elements, where the 3D or 4D or 5D shells are being filled up, these all have rather similar properties too. They're called transition elements. And they all have this property that the 3D shell is partially full, but the 4S shell, which is further out, is completely full, okay? And so the influence, the exact number of electrons that are filled in each of these is a little bit less critical in determining the chemical properties. Moreover, it's very easy to sort of rearrange the electrons, which orbitals are filled and which are empty. And that gives the transition elements their special properties. The situation is even more accentuated for the rare earth elements, the 4F and 5F metals. In this case, the partially filled shell is in the n equals 4 shell, whereas the n equals 5 and n equals 6 shells are already occupied. So these unoccupied levels are sort of buried deep within the atom, and they're shielded by the electrons in the outer orbitals. And that makes the chemical properties of these elements very similar to one another. It makes them difficult to separate from one another chemically, okay? It also makes them, the transition elements, and even more, the rare earth elements, it gives them the property that they can be magnetic, we'll talk about next. Oh, and finally, I just wanted to show you one piece of data showing how the chemical properties of elements are in the same column are similar. So this is a graph of ionization energy versus atomic number. And there's some interesting patterns. First of all, you'll notice that the ionization energy of all the elements that are in the first column of the periodic table, lithium, sodium, potassium, rubidium, cesium, they're all very low, okay? So that's a similar chemical property across all of these. These all consist of filled core shells of electrons, and then a single electron that orbits this nucleus and the filled core shells. And in that case, the single lone electron is relatively easy to strip off. On the other hand, if we look at the elements on the opposite column of the periodic table, we find a completely different story. Helium, neon, argon, krypton, they have very high ionization energies. It's very difficult to strip off an electron. In this case, the electrons completely fill the outermost shell. So these elements are difficult to ionize, takes a lot of energy to pull an electron out of this filled shell, and it also means that they're chemically inert. They don't participate in reactions with other elements because of this high ionization energy. Okay, very good. Well, that was a whirlwind tour of the properties of multi-electron atoms. Let me stop the share. Properties of multi-electron atoms. I'm just trying to give you a flavor for that and show you how it's connected with the properties of the hydrogen atom. Okay? But although this is a fascinating subject, some people call it chemistry, we're not going to talk about it much further. Instead, I want to talk in more detail about electron spin today. And then we're going to finish up our discussion of atoms and move on to talk about atomic nuclei next time.